Is it are we going to have diffusion coefficients that depend on space, like on the spatial coordinate?
Yeah, it's not that uncommon. So you have to be very careful about how you do your analysis and stuff.
Can you still average over a single trajectory?
So you have to be careful how you do your average. Yeah. Okay, let's get back to it then. So you remember where we ended off last week? Oh, and also don't forget we have those workshops on Friday. Okay, so if you struggled with the assignment, what we actually did on Friday was we wrote the program to do the simulation, and we wrote the program to actually do the analysis as well. Okay, cool. So come to the workshops. It's your chance to get that done. Okay, where were we? So remember what we were talking about? We started with F equals ma, molecular dynamics. We got rid of the solvent. We did algebra dynamics by adding a drag and random term. Then we went to Brownian dynamics by dropping the inertial term. We just took our system to the overdays. Okay? And that was the BD simulations we saw last class, and they were pretty straightforward, very straightforward to program. And we saw a really interesting connection between the stochastic differential equation and the partial differential equation, which was, of course, just the diffusion equation. Cool? And so that's where we left off. So now I want to take it one level even above Brownian dynamics, and I want to talk about Monte Carlo simulations. Okay? So first of all, let's think about what we have. Okay? So so when we talked about BD, remember we noticed that the velocity is ill-defined. Okay? There's really no velocity. Okay? Because as opposed to longevity dynamics, where a particle has a velocity and then if the force is applied, then there's an acceleration that changes that velocity and the particle can end up with a new velocity. But here we really just had particles jumping around randomly. Okay? And there was no correlation between those terms. So we're still following the idea of, BD still comes from our equation like this, plus our random term. Let's just do it in one dimension. And then what we do is we drop the initial term, and so we end up saying, okay, the delta x over delta t, which is our velocity, okay, is equal to the random term, sorry, no negative there, over z, the friction coefficient. Cool? So we just end up with the particle jumping around according to this. Our derivation is still from the differential equation, okay, but where we end up is with the particle just jumping around. Let's remember the coefficient for this guy here. We can rewrite this as 2atz over m squared delta t. Sorry, over, there's no c8. Well, let's just leave out the delta t for now. Let's put that in. Cool? Everybody all right with that? So we have this random number here. This means that our step size is, there's a distribution of step size, right? If we do it the fully proper way, this would be a Gaussian. As we saw in the workshop, we can actually use the linear distribution of this because of central number. Cool. So all we really have, though, is a particle that sits out of position. It jumps in a random direction, and it has some average jump size dx. Okay. So let's think about a different way of doing this simulation. Okay. Instead of having our x, y, and z positions, a differential equation, an equation of motion that we numerically integrate, let's just literally take a particle at some position, pick a random direction, and make it jump some distance. Cool? When we do that, we make the transition from Brownian dynamics to Monte Carlo. Okay? That's all Monte Carlo is. It's a purely stochastic thing. You say there's some probability of something happening. In this case, there's some probability that it jumps in a certain direction. Cool? All right? So in order for these to be fully equivalent, it means that our average delta x must be 2d square root of t z at t, where z at t is our usual zero mean and standard deviation.
I'm not sure I'm clear on the difference. It's just the position is what's randomly generated, as opposed to the velocity.
So what you would do in a Brownian dynamics simulation, there really is no difference. Okay, it's just a slightly different way of thinking about it. Okay, so what you might do in a Brownian dynamics simulation, you consider a particle here, right? It has some x position, and let's do it in 2D and y position, right? And then what do you know? Well, mx double dot is equal to, let's just leave it as r of t, right? And we have the exact same thing in y. And then we drop this, and we can solve delta x is equal to negative, sorry, r. Well, now let's put it in terms of this guy. We did this derivation last class. Okay, and we do the same thing in y. Cool? This really comes right from the equation of motion. We just assume over dynamics. That's it. All right? Monte Carlo, what we're going to do. And then, so this gives us some delta x, and it gives us some delta y, and then this is what our jump looks like. Okay? And then we do that again, and we get some different delta x, and some different delta y, and we get a totally uncorrelated jump over here. Cool? And these can be different because this can have some distribution of similarity. Cool? We can do the exact same thing by instead just saying, okay, we have some particle here. It's going to jump some distance, okay? And I can quantify what that distance is going to be on average. I just have to make sure it's equal to this. Cool? So it's just going to jump some average distance, delta r, cool. Then we just have to pick a direction. So if it's in 2D, we just have to pick some angle. Okay?
Again, randomly.
Again, randomly. Okay. Cool. So it's the exact same thing. That's the point. Okay? But in one case, we have our nice equations of motion that we derive all of this stuff. We pick two random numbers in order to get our delta x and delta y. Here, it's purely probabilistic, not really basing it on any equation of motion, except we're saying it's got to be this. But we just picked some random number for the delta r, and we picked some random direction for the jump. Cool. Totally the same thing. Yep. That's the point of this. Is to make the connection between Monte Carlo and Brownian dynamics mean exactly the same thing at this level. But it's a different way of thinking. Okay? And we'll get to that later, because when we start talking about purely probabilistic models, then we can start to get into all sorts of crazy applications, right? Like a particle going by and it has a chance to radioactively decay as a function of time and things like that. Okay? No equation of motion there. We can just use our probabilistic ideas that we're going to start developing here to solve that system. Matt was first.
Just to confirm, both methods need two random numbers, right?
That's right. Okay. For now. Well, no. How about if we go to 3? How many random numbers do we need here?
3.
How many do we need here?
2.
No.
3.
Yeah. Now we have another angle.
Yeah,
Yeah. Word of warning. if you naively pick those angles, you can bias your sampling. Okay, if you naively pick theta and phi, what you do is you end up like it's like a globe. You'll pick more points near the pole. Okay, so you have to be tricky about how you actually pick those. Mark?
The equations for average of delta x and average of delta r. So do we want, first off, is there supposed to be a random variable in the one on the whiteboard?
So this guy isn't an average, so yes.
Yeah, that one's okay, but over there it's an average.
No, you're right.
So, and is the average 0 or is it what?
I'm being a bit sloppy here.
Okay.
Okay. Because what it is if we just look at like the absolute, it's more or less the absolute value, right? It's just the size of the. Okay. So if we take just one time step, what's your jump size on average? Okay. So this is what it is.
Okay.
Cool. Right. So just for a delta T1, so we're not averaging over a bunch of jumps where everything has to cancel out over on the sample or whatever. Right? You just take one jump and you just look at how far you went. That's what it's. Okay. Cool. But you're very right to raise objections there. But if you believe me, then let's go one step further. Okay. Let's say I don't actually care about having a distribution of jump sizes. Okay. I just want to make sure I get the average quantities. So I can just fix my jump length to be in one dimension if I come back here. Delta x or delta t equals 1 to b to the square root of delta t. Okay, and of course this is 1, so we just get square root of 2. Cool. And now we get rid of that second random number. So in 1D, what am I proposing to you? Well, I'm setting up a simulation. I start the particle at some position. And what happens next? It jumps. So what do I need to do to figure out where it jumps and how far it jumps?
In BD?
No, Monte Carlo.
With the fixed step size? Flip a coin.
Flip a coin. Okay. What we've done is remember, as soon as we fix the step size, then we don't need a random number for that. We only need a random number to determine the direction. And in 1D, what are your possible directions? Left. Yeah, right or left. That's it. Forward or backwards. Is everybody okay with that? So our simulation really is we just have to draw one random number, decide if we jump this way or if we jump this way. Cool. So there's going to be some probability of jumping forward, let's call it T plus, and some probability of jumping to the left, T minus. And if that happens, then we don't need to know how far we jump because we fixed the jump size. So I would land here, and I would land here. And then I can repeat this, and my possible sites are all going to be the same separation. Right? In other words, I'm on a lattice. Okay? So when we fix the jump size well, you got to be careful, okay? But in 1D, then you get lattice Monte Carlo. Things are more subtle in 2D and 3D, but the same arguments. Okay? And in fact, we can actually extend it quite easily in 2D and 3D because we just also have a probability, an independent probability of jumping in Y that has the same lattice. Cool, and then we can bring in 10. And then you can bring in Q if you want.
Does that do something weird to our expected size? Like, do we have to reduce the step in X and Y in order for the step in R to be that?
No, because that's in, no, it washes out, okay? Because that's why we have the delta R squared is 2 little t times big D times
Oh, yeah,
t,
okay, we got it.
right?
Yeah.
So the prefactor is in there.
Right.
Cool? Everybody all right with this?
But this is a totally discrete jump steps. Like there's nothing
Yeah.
continuous about this. Like you can either be one dot or the next dot. Nothing else.
That's all right. Yeah. But we already lost the continuity when we dropped that inertial term, right?
Right.
We went to a whole bunch of just random jumps. The only thing is now we're saying, oh yeah, they're random jumps and they're all the same size.
Even though we define a step size, it still doesn't random walk.
Yeah, it's totally a random walk, but the randomness comes solely from the direction. Cool. It's like if we go back to our drunk stumbling around after the bar, okay, not only does he sometimes stutter step and then take big long steps like this, okay, but he always takes the same step size. It's going to be a random walk. Cool. Yeah? Yeah. All right. Is this all right with everybody?
I have a question. Is there a fast way to generate a coin flip rather than a full float random number in C? Or
No, you need a random number.
yeah, okay. I couldn't find one on Google either.
No. You got to get your randomness from somewhere. That's actually the best way to do it.
Seems wasteful, but yeah.
Yeah. You got to do something. I mean, you could develop some algorithm maybe to look at, multiply a bunch of independent numbers together to get some number, and then.
But it's easier, right, than getting a full continuous random number. Like it should be. It's just there's less information in a coin flip than in a not randomly generating a number with 0 and ran it back. So it just seems like there should be a faster way of doing it. But I guess it's so fast.
Yeah, no, it doesn't. Yeah. I think in the olden days they would have tables of random sequences that they could look up and walk through. Okay, but now we just let the computer handle that. And the thing is, those random number things have already been optimized so much. Yeah. Not necessarily the ones we're using, okay, but other ones you have access to. Cool. Okay, so let's take an easy example, and we're going to talk about a particle. There's no external field. So what do you think the probability should be equal to? Yeah, 1/2 and 1/2. There's no bias in the system. Okay, so this is a pretty easy program. All we need to do is put a particle out of position, draw a random number between 0 and 1. If it's less than 50%, let's say it jumps left. It's greater than 50%, it'll jump right. That's it. And always by the same step size. And what's nice about this is you can actually do integer math for this. You only need to keep track of the index of your lattice that you're on. Okay? Whatever your jump size is, you can always add that in later. Right? The important information is if this is 0 and this is +1, this is -1, this is +2, this is -2, etc. Cool? Okay, so let's see what this looks like. Awesome, Kyle, thanks. Okay, so I think this is Monte Carlo, yeah, so this is Monte Carlo code for 10,000 particles. Okay, and I've set all the initial positions to be equal to 0 somewhere. When I initialize the arrays, yeah, x is equal to 0 here. Notice that I don't have any velocity in here. I don't have any acceleration in here. All I'm going to do is evolve the position directly. I'm going to have a distribution here, rho, that I'm initially going to set equal to 0, because what I want to do is keep track of the number of particles at each position. Okay? We're not particularly interested in any one trajectory right now. We just want to know what the distribution looks like. In fact, we already know what the distribution should look like, right? What should the distribution look like? Yeah, exactly. The Gaussian, according to the Walker plank that we looked at last class. Okay? Because remember, Cal's question, how is this different than BD? It's not. Okay? It's exactly the same. Well, we have a fixed jump size here. What you would expect if you have enough jumps, that's an average. Okay, and that's it. Yeah, if it's, so I pull a random number. If rand is less than 0.5, I'm going to the left. Otherwise, I'm going to go to the right. And that is it. That is the sum of our simulation. Cool. And so this is obviously very, very fast. They were barely doing anything. And like BD, we also don't have the restrictions on the time unit that Longitude Dynamics has. Cool. Again, for non-interactive.
Well, wouldn't we still have some kind of, like we kind of, I think in way DT, we've assumed that the step in every time step is yeah, so we've implicitly set the scale of the problem.
Absolutely. Yeah. But the algorithm doesn't break down as you make that DT bigger.
Right, but if we were interested in phenomena at a certain scale, we have to make one of those parameters important.
Yes, you still have to be correct in your modeling, right? But there isn't an algorithmic constraint on how big your DT can be. But there is in Longitude Dynamics. Yeah. Cool. All right, so super easy. This code runs really fast. What do the results look like? So, do the Okay. So previously, this is a result we looked at last class for the Brownian dynamic simulations. Remember when we got this? We got that. Whoa, I'm on the wrong screen. And we got this cool agreement between the BD simulations and the Fokker-Planck solution. Right? You remember seeing this?
Yeah.
So we're aiming for the same thing with our Monte Carlo. Blah, blah, blah.
So many error messages.
No, it's all just because I stopped it. And this is what we get. So green is Fokker-Planck, and blue is the Monte Carlo simulation.
Okay, that's fine.
So there's something pretty wacky going on here.
It looks
Does anyone, not Martin, want to guess what it is called?
I don't think you gave Mark the choice to say.
Right. So that's the answer, and we'll talk about that much later. Okay. Actually, not much later. Maybe later today, or tomorrow. That's much later. Okay. So Paul's absolutely right. Okay. The way of solving this is to introduce a third probability, which is the probability of sits. Okay. But what's going on? What's causing this? It's causing these crazy spikes.
Well, they're not necessarily crazy. I mean, the Fokker-Planck is continuous for us. That's just discrete. So that those points still fall in the same
Really?
shape.
They're not crazy? So if you start particles at 0, you're telling me that at some time later, there's absolutely exactly 0 probability that will be at this location.
I guess I shouldn't say there's
Spikes.
zero. There's zero probability, but you can have something there the next time.
Why is there exactly 0 probability?
Did you take the average?
Average of what?
I'll get back.
They're moving both.
Anybody? So let's go back to our algorithm. Anybody? Okay. So we start with all of our particles at this location. Okay? And then what happens?
It goes left or right.
Goes left or right. So if we start with 100, how many go right?
Say 50.
So about 50, right?
Oh,
How many go left?
And then you have none in the middle.
You have none of them. Okay? So this is the odd-even problem of Monte Carlo simulations. Where everybody's jumping all the time and you start at the same location, then your access to the sites actually depends on whether you've had an odd or even number of jumps. Cool. This is not physical. That you start everybody here, half of them jump like this and nobody's left. Okay? Another way to solve this is to have a distribution of jump sizes, right? Which again brings in probability of a jump size of 0. Okay? And then you can have some left. But we don't want to bring in a distribution of jump sizes, then we need another ring.
But you know, if you just bend it to have bends that were 2 steps wide.
Sure, there's another way of doing it too. Just average over any 2 consecutive point steps. Yeah, Matt, it's not enough to just say average.
I know.
And then you're right.
I'm so angry.
Okay, so let's do that. Let's just average between 2 time steps. So here I'm plotting the same thing, except I'm just summing up 2 time steps, dividing by 2. Cool? All right, so let's see what that looks like. Okay, and we get our nice agreement back. Okay? Cool. So we can do Monte Carlo simulations of a random walk, and it's super, super easy and fast. We only need to draw a random number. And notice here, it really doesn't matter what distribution the random number is from, right? So even distribution, which is uniform distribution, which is the fastest problem, is totally okay. Yeah, and we can actually still get back our nice random walk behavior, our diffusion, which is what we've been trying to get to in everything we do. Yep.
So super, we take the average of 2 time steps or all time steps?
No, just 2 consecutive, because it's odd and even, right? So if this is 0, both of these are 1, then at t equals 0, you can only be on odd numbered or even numbered. When t is even, you can only be on even numbered sides. When t is odd, you can only be on odd numbered sides. So you just average the 2. Cool beans. Any questions on that? Okay. Let me try and find something.
But we have
Okay, I can find it.
Places that cannot.
Okay, so the next topic we're going to talk about is non-equilibrium simulations. Okay, but before we do that, let's just reflect back on what we've been studying so far. Okay, fusion is kind of weird. Okay, it's not like ballistic motion at all. How is it not like ballistic motion? Anyway.
We have to make sure that at any given time step in diffusion, you're not correlated to where you're going or where you're coming from before.
Yeah, that's true. So what does that imply?
Diffusion is a random walk.
Yeah, what does a random walk mean?
well, so the mean square displacement goes up to the square root of t instead of t.
Not the mean square displacement.
Square root of the mean square. So yeah,
Right. Yeah, that's true. But more fundamentally, a very simple idea.
ballistic is deterministic. Diffusion is random.
Yeah, that's really good. If I start a bunch of particles, say at the center, and let them go and there's no force, but they have a thermal motion, right? What happens to them?
Well, they spread out, but there's a couple of characteristics in that cloud that we know.
Right.
Mean being zero.
Equals zero.
Square distance.
Okay? If I take a bunch of tennis balls, hold them in my hand, let them go, drop them, okay? All fall under gravity in this direction, okay? And so there's a net displacement to that entire group. Cool? If I take a bunch of particles and let them go under diffusion, there's no net displacement for that group of particles. And then you go this way is this way, okay? And then you go this way is this way. Cool? Particles kind of don't go anywhere, right? Mean zero. Well, they do go somewhere because the cloud is spreading, right? The particles kind of don't go anywhere, but they totally go somewhere. Okay. There's no average displacement. There's an average mean square displacement. Okay. And as Martin already said, mean square displacement scales as t. And so if you're to take the square root of that to try and come up with some characteristic distance, that characteristic distance, i.e. the size of your cloud, scales as a square root of t. Okay? So if you have a bunch of particles, how far have they gone? Well, it's linear in t if the velocity is constant, right? But when you have diffusion, they initially spread out very fast. Okay, but as time goes on, slower and slower and slower. Okay? So it's very different from ballistic. Cool? And it all comes from this randomness. All right? So ideas about diffusion coefficient, mean square displacements, very handy whenever you're talking about simulations or any stochastic process. Cool? Okay. Next topic, non-equilibrium simulations. There. So what we want is a particle, okay, that still has some temperature kT associated with it. All right. And we're going to start with Langevin dynamics. We don't want to do go back all the way to molecular dynamics. Too many particles. Okay. So it's still going to have a, let's say if it's got a velocity like this, it's still going to have a drag force associated with it. And it's also going to have a random kick force in here. Cool. And so if I write down the equation of motion for this particle, what's it equal to?
We'll just do MA, so MX pop up.
Yeah, well, let's do it in general dimensions.
So we're going to have our old KT2, which is our zeta.
Well, that's the damping term, right? Drag force.
Yeah.
Right. Negative zeta V.
We got our random term still.
Yeah, and let's write it in the form. We can just leave it like this, right? Where we know something about the property of this, right?
And now we add in any of it.
Yeah, so to generalize this, having an external force in the system is really, really easy. You just add in what that force is equal to. Cool. You just add it to the equation of motion. And it can depend on our position R. If we have other particles in the system, it can depend on any of their positions as well, right? It can depend on, it can also depend on time. We don't care, right? As long as we can figure out what it is, at the point we have to calculate the acceleration. Okay, so then our acceleration is just 1 over m, this f, which really can be as complicated as we like. Cool. In addition to the f does not change the noise character at all. Okay, all the usual things still apply. The mean of r is still 0. Okay, and then we have this thing. Okay, so that the variance is 2 kt zeta, and you have uncorrelated between Cartesian coordinates, and it's uncorrelated in.
So does that assure stuff about force? I mean, for instance, if you've got if the random term is coming from your solvent, and the force is some electric field that also affects the solvent, doesn't that change the random force?
That is not built in to our usual thing. There's no hydrodynamic component.
So the force, what does the force have to do? Like, what kind of forces allow for this? What don't? Like, I mean, what kind of forces would violate this? Well, the force can affect the random term, can't it?
Yes, it could. Yeah, but most often, so if you just take a box of water and an ion in it, and you apply an external electric field, this is actually pretty good. Okay.
What exactly is that random? For what, sorry?
So R is the random force. So yeah, you missed a couple lectures. Yeah, okay. So this is just like we're trying to model the effects of the solvent implicitly instead of having a whole bunch of other particles that act as a mass of particles. Tell you what, we'll talk. Yeah, cool. Yeah. Is this cool with people? Okay, because this means it's really easy to do our simulations. Okay, because this is the beauty of MD, LD, and ED. We can take any force and just add it to our simulations so easily. Okay, it can depend on crazy things. Doesn't matter as long as we can evaluate it to get the acceleration, numerically integrate, we can solve the problem. Cool. This is in fact why we do simulations. Okay, because to add crazy forces to this stochastic differential equation, it becomes very, very hard to solve. ED, same story. We would have our delta x over delta t going to be equal to, or sorry, I gotta be careful here. Going to be equal to force over zeta plus the random term over zeta. Cool. And so what does this become? We do it in one dimension. We get what we had before. We just add an extra term at the front, which is just the force over the friction. The zeta. All right, this definition allows us to do something. We want to calculate the average position. Or sorry, the average jump size. Okay, for a single time step. And actually for any time step. What do we get? Well, what's the average of this thing? 0. Okay? So what are we left with? We're left with this.
Why is that 0?
The average of the random term must be,
Oh, 0, yeah.
yeah, must have 0. Cool. What this does is this allows us to define a,
Wait, are we missing a delta t there?
yes. So the easiest way to see it is actually not include the delta t on this side yet.
Here, can we see this one?
So delta x delta t, right, is equal to this.
With a delta t and the square root?
If we, it depends if we've discretized it or not. Right? Cool. All right. So if we take the average of this side, and we take the average of this side, everything here is constant. We take an average here. What do we end up with? What's this equal to?
Fx over there.
Yeah, so we'll delta x delta t is the velocity, right? Cool. So this is allowing us to define a certain velocity here. That velocity is going to be fx over zeta. Okay. And so this is a specific velocity. It's called the drift velocity. Okay. So the idea here is we'll see it in some simulations in a minute. Well, let's say we have a particle in 1D that both has a drift term to it and it has a thermal noise. Okay. Well, what does it look like? Well, the thermal noise means it's jumping around like this, right? The drift term means that it's moving in some direction. So the thing is moving around, is jumping, but over time it's drifting in one direction. Cool. The rate at which it's drifting is just given by the force in that direction over. Cool? Yeah? We'll see that. Okay. So before we look at simulations of this, let's try and make a connection back to our Fokker-Planck formulation. Okay, remember that where that comes from. We looked at Fick's law, and we looked at having two different types of currents that we derived kind of demonstrated the diffusion. Okay? And what did we get? Well, we started from a continuity equation. Okay, which said how the distribution of particles is changing in time is going to be related to the divergence of the flow of those particles, the particle current. Cool? Continuity equation. And previously we said, okay, well, this current arises from Fick's law, right? If our distribution is not uniform, there's going to be some gradient. Particles will tend to go from the high distribution to the low distribution. And the rate at which that happens is a proportionality constant, and that exactly is our diffusion. Cool? So if you pop that in there, you get the diffusion equation, right? Because what you're going to get, well, if D is not dependent on space, you're going to get negative D, the Laplacian of the distribution. And that is the diffusion equation. Okay? The heat equation is which all you should. Okay? But now we have an extra term in here. We don't have a non-zero drift anymore, right? There's a current. Particles are moving because of this external force applied to them. Cool. What's that going to contribute? Well, at any position, it's going to be the velocity of particles there multiplied by how many are there. Cool. That's all right with people. So what this means is that our new equation looks like, oh, incidentally, this assumes there's no sources or sinks. Particles are not magically appearing, nor are they magically disappearing. Okay? Okay, so what does our equation look like? Well, we can pop that in. All right. Let's simplify this a little bit, not a ton. Cool. So this is no longer the diffusion equation. This is the convection diffusion equation. Okay? Because now no longer do we just have diffusion, but we also have some drift. Cool? Yeah? Okay. So this is closely related very slightly different form. Okay, in 1D. I'm just doing it in 1D for now. We're going to program it.
So that form assumes that D is independent of space, and that form has independent.
We actually haven't made that assumption yet here, right? Because we haven't carried through the divergence yet.
But so if it is dependent, then how did we get it inside the derivative?
I'm not saying these are identical right now.
Oh, okay.
Oh, very closely related. Per tell, these are formally identical, but I have to work through the vector calculus.
Yeah, but there's some trick there maybe.
Yeah,
Yeah, so they're not supposed to be.
it's not obvious. Okay. So I think they're identical, but for at a minimum, let's just say they're very closely related. Okay. And so this is a confusion advection equation. This is the Fokker-Planck equation with drift. Okay, and then certainly for the special case that D is independent of X, you can show these are identical. Okay? When D is not independent of X, well, we get into the really hairy stuff we've been talking about, like if you have a particle diffusing in homogeneous media. Okay? And then in order to get this identical to that, you have to add another term which basically amounts to a bias at the surface. And that's where you get into the different calculi, Keto, Stratonovich, and so on.
That's for inhomogeneous medium. That's just inhomogeneous at a boundary. Like it's just continuous, but on either side it's the same.
No, wherever you would have a change in.
But what about a continuous change?
Yeah, no, that's still. Whenever the derivative of D with respect to X is non-zero.
That just comes out as a boundary.
You can add it'll be an extra term to this, right? I think you can. I think that's where these aren't identical, but they can be identical formally. We have to add that extra term, which amounts to a force wherever the gradient of D is.
Oh.
Cool. That's where you get into the different calculi, which again is a very good project topic. You guys should really start thinking about project topics. Okay? Don't leave it until the very end. All right. Cool. People okay with this? Mostly. Okay. So we're adding drift. Now this equation here, Fokker-Planck with drift, very famous, very wide usage of it. Two examples. Navier-Stokes, the flow of an incompressible fluid, has the same form, almost the same form. Okay, where m is the momentum of the fluid at any point. P is the pressure, and F is any other forces we have here. Like gravity or something. Okay. And perhaps an even more famous application certainly more deadly application. Anybody recognize this? This is the Black-Scholes equation. Anyone heard of that? It is the only thing holding up our economy and the financial markets. Everybody has decided that this is how they behave. Okay. What is it? What are these different variables? Well, S, price of the stock. Okay? And D is the price of an option. That, you know what an option is? You should. It's basically betting.
It's like just like you're buying credit, right?
Huh?
It's like you're buying credit. You're option to buy this price versus the option to buy another price.
Anybody? Option? No day traders here?
Option to sell and buy, you can basically bet on whether the stock's going to go up or down over the next day.
Yeah, so you don't buy the stock, but you buy the option to buy the stock. Okay?
At the current
You
price.
give, exactly. You give some money and you say, okay, I just want to reserve. You got to hold these stocks aside, and then over a certain time period, I just want to pay you to reserve the right to buy them at the current price at the end of this month. Okay? And then there's different ways of doing it. European, you have to wait until the very end and then make your decision. American, you can buy any time before the end. Okay? But it's basically like betting. Okay?
You can do the same thing for selling. So
Yes.
you're gonna sell these at the
Call.
current price.
So call is buying and put is selling.
Then somebody has to buy your grossly overpriced stock, and therefore.
Exactly.
And things like R's and Sigler.
So we'll get to those, okay? But obviously, we're interested in knowing, well, if I can figure out what like the actual value of that, the real price of that option is, right? So we want to know how the price of that option changes with the stock price. Okay? Because obviously that's our independent variable, right? It's going to go up, it's going to go down. So what are these different things? Well, this is the volatility of the stock price. In other words, how much does it fluctuate up and down? Does that sound familiar? How do we characterize how big the randomness is if we have a random walk? The diffusion coefficient. Cool. So this is playing the part of D. Right? The volatility, how much jumping up and down, well, that's exactly our diffusion. Well, not exactly, but exactly the analog. And how about R? Comparison to our form, what do you think R should be? So what is R in our Walker Planck?
The drift.
Yeah, it's a drift. So in our financial model, what might be our drift? Okay, so stock prices are going to fluctuate. This says there's also a drift term, right? So it's the amount that they're safely assumed to go up with time, presumably. Okay, so this is the risk-free interest rate. This is how much is just naturally going to grow with interest. Cool. So this Black-Scholes equation that they use to value options is totally just our diffusion equation with the drift term. That's it. Okay. And that's why there's a lot of physicists and applied mathematicians making money on Wall Street. Now there's entire programs in quantitative finance. Okay. But a couple of guys I was in grad school with went on to do like risk analysis and stuff like that for banks. Okay, PhDs in physics.
What are BNS?
S is the stock price, and D is the option price. Cool. Pretty interesting parallel. How good is it? That's a very scary question. And this is an absolutely excellent topic. Okay. So what's neat about this? So in this course, and what have you learned? Okay, so we got to this analog, but you now know methods for solving this. But we'll talk about what solutions for this partial differential equation looks like, right? But even if we have a PDE that is too hard to solve with any reasonable accuracy, what's another way we can go about studying the system?
Oh, the stochastic method.
Yeah, we know that this is exactly equivalent to a stochastic differential equation, right? So instead of trying to figure out the distribution, the means of these option prices, let's actually just do a whole bunch of independent trajectories. And then we can calculate the averages from that. Okay, so again, this is moving from a continuum model towards a particle-based model, an agent-based model. Okay, cool. And in this class, you're learning those agent-based approaches. Cool. So it means when we talk about balls bouncing around between walls, you're like, I really don't care about balls and walls. Okay, it totally could be a stock price. And in fact, it can be as abstract as you want to. We're going to see techniques that actually use, you can develop simulations of how people come to decisions. Okay, they have certain information, they bounce back and forth, and then they'll make a decision, right? Kind of like a random walk with Rick. So all sorts of abstraction you can do this way. You can actually describe it with these stochastic differential equations and partial differential. Cool.
So the Black-Scholes is not actually known to be correct, right?
It was
We
made
don't
in
prove that
1976.
that's correct. Nobody's really validated.
There's been around 40 years. I don't know.
So
And also how you
let's totally table this discussion. And hopefully someone will do their project on this, and they can tell us all about that. Okay, because it's quite controversial, really. It's widely used, but there are questions.
I read the Wikipedia, and there's some free guys for some assumption.
Yeah.
Wow.
Cool? Okay. And so, obviously, if D, let's see, blah, blah, blah. If things here, so if we go back to our bucket plan, if things like our V is changing with X and T, and our D is changing with X and T, this is going to be very difficult to solve analytically. Okay? That's when we can just do the simulations again. Cool. But to convince ourselves that this equation is correct, let's simplify it so that we can get an analytic solution. Let's compare simulations, so particle-based SVEs, against continuum-based distributions from PDEs to make sure it still holds true, like we did for the diffusion. Cool? Yeah? Anyone understand that? Yeah? Okay, so what we're going to do is take this equation, make some simplifications. Simplifications we want to make are that D is not changing and there's a uniform field so that there's no divergence to our V. Okay? So what we get then, that d rho dt equal to D, little Laplacian of rho, which is just our diffusion equation. And then we have this exit term, which is the dot product between the velocity, drift velocity, and the gradient of rho. So 1D that. That's a differential equation we can solve. Anybody want to guess what the solution to that differential equation is?
I'm guessing that's shifted by
Okay, so good. Let's start with what we already know. Let's build up on our Gaussian. Remember our Gaussian for just the diffusion equation looked like this. Cool. The mean of this was always 0. And the width of the Gaussian spread out in time. That's our variance here, 2bt. Cool. Now that we have a drift, what's going to change?
well, they're kind of two separate terms. The first term being the Gaussian is still the Gaussian, but then we're going to have essentially just consistent velocity pushing everything along a direction.
Right. Well, how can I include that in here?
Can we do just like plus BT kind of thing? That's right. That's
Yeah, that's it. Okay. And so these are really uncoupled. What this says is the mean of this thing is just going to move along at some constant rate, the drift rate, which is totally what we expect, right, from a particle. And if we're in the frame of reference of the Gaussian, so we're moving along with it, all that's happening is diffusion is making us spread. Cool? So these neatly separated into their two different components. Yeah? Yep. Okay. Where is this? Okay, so here's what the code looks like. And again, this is going to be a super simple program. Okay, I'm just using a Gaussian random number here for my velocity, quote unquote.
We're gonna need no. The projection.
Oh, the projector's off. I can't do that.
I think it actually
Turned off. Is it red light?
it made a noise.
Oh, I think green light.
fix it. Fix everything.
Okay, well, we're waiting for that to warm up. I want to talk about something else as well. So this is our program. Here's my velocity, which is just going to be f over g plus my prefactor times Gaussian. It's exactly like what we had before. I'm just adding in force here. Okay, so that's it. That's all my simulation is. And I'm just going to keep track of where my particles are. Okay, so this is exactly like the code we saw before, except I'm adding this f over g here. That's it. Okay, so what change does that make? Okay, we're going to plot it here. You need the force of 3. Okay. And so we see our Gaussian again spreading as before, but now it's also green. Okay, and green is Fokker-Planck, and blue is my distribution of particles from the Brownian dynamics. Okay, so again, we have really good agreement.
Lagging a bit. And
Yeah.
it fluctuates above green on the left, but always below green on the right.
Yep. Cool. You can get niggling details like that depending on how you fit your hair. You have an offset of like half of it, right? Okay, so cool. That works. Of course, we're interested in, we're not always interested in, you know, plotting these distributions to get our values. We also sometimes just want to calculate them. And so how can we calculate our drift and diffusion? Okay. So remember before, when we had no drift, what was our mean x position equal to? 0. Now what is our mean x position equal to?
Drift velocity time.
Yeah. VT. Okay, where V is the drift velocity. So if we go ahead and calculate delta, the average of x squared, okay, previously when our mean was 0, we could use this to get 2 dt, to extract the diffusion coefficient, right? What's going to happen if we do that now?
We need to subtract that.
Pardon me?
You get some profit.
Well, what's going to happen is that before, when everything was at 0, we were just looking at the clouds spreading out. We can calculate the mean squared displacement, add them all up. And from that, plotting that versus time, we could get, right? But now the cloud is also spreading, right? So now the mean squared displacement is naturally actually going to be growing in time due to that, right? And so we're going to get massive numbers for our diffusion coefficient because we're including the drift. Cool. How can we correct for that? Yeah. From any particle, we can just subtract off the drift velocity. Okay? And so now again, our cloud will just be centered at 0 and drift again. Cool.
Isn't that just when we're calculating the variance of x, that's the second term?
Yes. Okay? This is exactly equivalent. Remember, d is the variance of x, the square of the standard deviation. So that means it is this, as we talked about. Okay? And previously, this was 0. Okay? But now it is no longer 0. Okay? So, well, I have to be careful here. So this is delta x squared. Cool? Okay, so I can do a longitudinal simulation. We'll do an LD simulation with multiple particles, okay? And I'm going to average over this, the displacement of all of them and also the square displacement of all of them. So if I do larger dynamic simulation, now my force is added to the calculation of the acceleration. Okay? I'm doing BD before and LD now to show you later. Right? And all I'm going to keep track of is my average x position and my average x squared. And this, when we had just diffusion, was 0, very close to 0 all the time. Okay? This guy is the one that goes in. Cool? So if I look at plots of this, okay, so the red line is the average x as a function of time. Okay? And I used a velocity of 5. And so we expect that the drift to look as basically 5 times speed, right? And that's shown as the dashed dotted blue line. Okay? So the mean position behaves as we expect. Cool? Yeah? And if I plot the mean squared displacement as a function of time, I get this guy here. Okay? And the mean squared displacement is really blowing up. And it's actually just the square of the previous term. Okay? Because drift is totally dominant over diffusion. Okay? So in order to get the diffusion coefficient out, what I need to do, and actually you can see it cool, if we do a log of that plot, okay? Start smaller, and so this would be your ballistic regime. All right? diffusion always wins at small time scales, which we'll talk about. But this is actually ballistic because there's longevity dynamics here. And then it crosses over to drift taking over, and we go to the scaling of the drift. And so in order to correct that, what I can do is just take the average square value minus the square of the average value. This is like subtracting off the drift velocity. Cool. And then what I get, if I plot that on a plot here, I get this nice straight line. If I do log, so I can see it here, so I can get the diffusion coefficient from this. If I do log, you can see it going from ballistic and now going towards this. Cool. All right, so we see both in the distributions and in the calculation of the moments of the distribution to get the diffusion that really our diffusion and drift are not coupled. Okay. We have drift, which is making us move in one direction. We have diffusion, which is making us spread out. So we basically just add them up. Okay. Mark.
Aren't you going to get really bad cancellation error? Just finding a big number from a big number.
Well, it's working right now.
Yeah, but in general, not a big risk here.
You have to be careful about how you do it. Cool. Any questions on this? That's it? Okay. So this is how we can add drift to our problem, which obviously greatly expands the physical systems we can look at. And as we've seen, it also greatly expands the other applications that we can look at. Basically doing both agent-based simulations as well as these continuums. Okay? But the continuum things get really hard to solve as things become complicated. It's a beautiful thing about agent-based simulations, make it as complicated as you want. I'll just put it in my simulation and see what happens. Okay? So we're going to talk about this a little bit more. When we come back, we're going to talk about boundary conditions. Okay? And what we can learn from simulations with different boundary conditions. That'll be tomorrow.